Short-term overheating, stress rupture damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of short-term overheating, stress rupture based on API 571. Permanent deformation occurring at relatively low stress levels as a result of localized overheating. This usually results in bulging and eventually failure by stress rupture. Short-term overheating leading to stress rupture damage refers to the failure of materials, particularly metals and alloys, due to exposure to elevated temperatures for a relatively brief period while under stress. This phenomenon is particularly significant in applications involving high-temperature environments, such as power plants, chemical processing facilities, and aerospace components. Characteristics of short-term overheating, stress rupture damage. Number 1 is mechanism. When materials are exposed to temperatures that exceed their design limits, microstructural changes occur. These may include grain growth, phase transformations, or the degradation of mechanical properties. Stress rupture occurs when a material is subjected to a constant load while being heated. The combination of prolonged stress and elevated temperatures can lead to the formation of cracks or voids, eventually culminating in catastrophic failure. Number 2 is temporal aspects. This type of damage typically occurs over a short timescale, hours to days, differentiating it from long-term creep, which manifests over years. The onset of failure can be rapid, as it accelerates with increased temperature and sustained load. Number 3 is consequences. If not addressed, stress rupture can lead to catastrophic failures in critical components, resulting in safety hazards, equipment downtime, and significant economic losses. Understanding short-term overheating and stress rupture damage is crucial for engineers and maintenance personnel in high-temperature applications. By recognizing the signs of damage and implementing proper prevention measures, the integrity and reliability of critical systems can be upheld, ensuring both safety and operational efficiency. Short-term overheating, stress rupture damage mechanisms affected materials based on API 571. All fired heater tube materials and common materials of construction. Short-term overheating can lead to stress rupture damage, particularly in materials subjected to high temperatures and mechanical loads. This phenomenon is especially critical in high-temperature applications, such as power generation, aerospace, and petrochemical industries. The affected materials typically include. Number 1 is superalloys. Used in gas turbines and jet engines, superalloys are particularly sensitive to overheating, which can induce changes in their microstructure leading to stress rupture. Number 2 is steel alloys. High-strength steels, especially those with significant alloying elements, e.g., chromium, molybdenum, can experience stress rupture at elevated temperatures. Number 3 is nickel-based alloys. These materials are often used in high-temperature environments and are susceptible to degradation under thermal stress. Number 4 is titanium alloys. Commonly used in aerospace applications, titanium alloys can undergo phase changes and reduced ductility at elevated temperatures. Number 5 is ceramics. While ceramics may not rupture in the traditional sense, they can degrade or fail under thermal and mechanical stress. Number 6 is composite materials. Polymer matrix composites, or PMCs, can be affected by overheating, leading to matrix degradation and interlaminar failure. When materials are subjected to short-term overheating, they can experience microstructural changes, loss of mechanical properties, oxidation, and increased susceptibility to creep, leading to stress rupture failures. It's important for engineers to monitor and control the operating temperatures of components to prevent such damage. Critical factors. Short-term overheating and associated stress rupture damage mechanisms are critical concerns in materials science, particularly in high-temperature applications such as in gas turbines, power plants, and other industrial processes. The understanding of these factors is vital for ensuring the integrity and reliability of materials under extreme conditions. Here are the critical factors influencing short-term overheating and stress rupture. Number 1 is temperature exposure. High temperatures can significantly affect the mechanical properties of materials, leading to softening and decreased strength. Exceeding the material's design temperature can accelerate damage mechanisms. Number 2 is time at elevated temperature. The duration of exposure to elevated temperatures influences the extent of material degradation. Even short-term exposure can cause significant changes in microstructure and mechanical properties. Number 3 is material composition. The specific alloying elements and phase structures in a material influence its resistance to overheating and stress rupture. Materials with higher creep resistance, such as certain nickel-based superalloys, perform better under severe conditions. The first of material composition is creep resistance. Materials exhibiting good creep resistance will generally perform better under high temperature and stress conditions. Understanding the material's creep behavior is crucial in assessing its susceptibility to stress rupture. The second of material composition is alloy composition. The specific alloying elements and their concentrations can affect the material's resistance to thermal fatigue and stress rupture. Elements that promote solid solution strengthening or cohesive strength at high temperatures can enhance performance. The third is cooling rate. The cooling rate after overheating can also affect the material's performance, as rapid cooling may lead to thermal shock and microcracking, while slow cooling might allow for some recovery. The fourth is heat treatment. Prior thermal treatments, e.g., annealing, quenching, and aging, can influence the microstructural stability at elevated temperatures, thus influencing the likelihood of stress rupture. Number 4 is microstructure. The initial microstructure of the material, such as grain size, phase distribution, and precipitates, plays a crucial role in its high-temperature performance. Coarse grains, for example, can lead to reduced creep resistance. Number 5 is stress state. The applied load and type of stress, tensile, compressive, shear, can affect the rupture behavior. High tensile stresses can exacerbate the effects of thermal damage. Number 6 is microstructural evolution. Elevated temperatures may lead to phenomena such as grain growth, phase transformation, and precipitation, which can negatively impact the mechanical properties and performance of the material. Number 7 is oxidation and corrosion. At high temperatures, materials are more susceptible to oxidation and other forms of deterioration, which can further degrade material properties and lead to premature failure. Number 8 is prior service history. The material's previous exposure to stress and temperature cycles can affect its current behavior under overheating conditions, including the development of residual stresses or damage. Number 9 is environmental factors. The surrounding environment, including the presence of gases or pollutants, can accelerate degradation processes, e.g., oxidation, carburization, under overheating conditions. Number 10 is load history. The history of loading, including any previous cycles of loading and unloading, can introduce residual stresses which may promote stress rupture under thermal conditions. Number 11 is fatigue. Previous fatigue damage can lead to the formation of microcracks that are more prone to grow under conditions of short-term overheating and sustained stress. Number 12 is presence of voids or defects. Any pre-existing voids, microcracks, or other defects can serve as stress concentrators, leading to localized areas of failure under external stresses coupled with high temperatures. In summary, short-term overheating and stress rupture mechanisms are influenced by a combination of thermal, mechanical, material, and environmental factors. Understanding these critical elements is necessary for predicting material behavior and designing components that can withstand high-temperature operations safely. Affected units or equipment based on API 571. The first is all boiler and fired heater tubes are susceptible. The second is furnaces with coking tendencies such as crude, vacuum, heavy oil hydroprocessing and coker units are often fired harder to maintain heater outlet temperatures and are more susceptible to localized overheating. The third is hydroprocessing reactors may be susceptible to localized overheating of reactor beds due to inadequate hydrogen quench or flow maldistribution. The fourth is refractory lined equipment in the FCC, sulfur plant and other units may suffer localized overheating due to refractory damage and/or excessive firing. Short-term overheating, stress rupture is a damage mechanism that occurs when a material is subjected to high temperatures and stresses, causing the material to rupture. The affected units or equipment of this damage mechanism are typically those that are exposed to high-temperature environments, such as Number 1 is boilers and heat exchangers. These are equipment that are designed to handle high-temperature fluids, which can lead to overheating and stress rupture. Number 2 is pressure vessels. Pressure vessels, such as those used in chemical processing and power generation, can be susceptible to stress rupture due to high temperatures and pressures. Number 3 is piping systems. Piping systems that carry high-temperature fluids or gases can experience stress rupture due to thermal expansion and contraction. Number 4 is turbines and generators. These machines are designed to operate at high temperatures and can be prone to stress rupture if not properly maintained or cooled. Number 5 is heat transfer equipment. Equipment such as heat exchangers, condensers, and evaporators can experience stress rupture due to high temperatures and pressure differentials. Number 6 is cooling systems. Cooling systems, such as cooling towers and heat exchangers, can experience stress rupture if not properly designed or maintained. Number 7 is refrigeration equipment. Refrigeration equipment, such as compressors and condensers, can experience stress rupture due to high pressures and temperatures. In general, any equipment or system that is exposed to high temperatures, pressures, or stresses can be susceptible to short-term overheating, stress rupture damage. Appearance or morphology of damage based on API 571. The first is damage is typically characterized by localized deformation or bulging on the order of 3% to 10% or more, depending on the alloy, temperature and stress level. The second is ruptures are characterized by open fish mouth failures and are usually accompanied by thinning at the fracture surface, see Figure 4, 28 to 4 to 30. The appearance or morphology of damage due to short-term overheating and stress rupture in materials, especially in metals and alloys, is characterized by several distinct features. Here are the key aspects of the appearance associated with this damage mechanism. Number 1 is cracking. One of the most prominent features is the formation of cracks. These can appear as brittle fractures, often with a characteristic intergranular or transgranular appearance, depending on the material and conditions. The cracks typically initiate at regions of high stress concentration or microstructural defects. Number 2 is creep rupture features. Visible signs of creep, such as elongation and necking of the material in the direction of applied stress. Internal voids or cavities may form due to the diffusion of atoms and the coalescence of defects. Number 3 is necking and ductility loss. In some cases, especially in ductile metals, there may be localized necking where the material deforms significantly before rupture. However, short-term overheating often reduces ductility, leading to more brittle failure modes. Number 4 is discoloration. Overheating can lead to changes in color on the surface of the material due to oxidation or changes in microstructure. This can include blue or golden hues due to heat tint. Number 5 is grain growth and coarsening. Excessive heat can cause grain growth, which can be visible as larger grains in the microstructure when examined under a microscope. This can reduce the material strength and alter its mechanical properties. Number 6 is oxide layers or scale formation. On the surface, there may be the formation of oxide layers due to prolonged exposure to elevated temperatures. These scales may vary in thickness and composition, affecting the material's fatigue life and corrosion resistance. Number 7 is microstructural changes. Short-term overheating can cause changes such as precipitate dissolution or reprecipitation, leading to a loss of strength. This may be observed in a metallographic analysis where the phase distribution appears altered. Number 8 is intergranular damage. For some materials, especially those that are more susceptible to such damage mechanisms, e.g., certain nickel-based superalloys, intergranular cracking can occur, which is characterized by cracks propagating along the grain boundaries. Number 9 is fracture surface. The fracture surface may display features typical of stress rupture, including a fibrous appearance or a more brittle, granular texture depending on the loading conditions and material properties. Number 10 is pitting and localized degradation. In some cases, localized damage may manifest as pitting or other forms of localized degradation, particularly in materials that are exposed to corrosive environments at elevated temperatures. Understanding these morphological changes is essential for diagnosing and assessing the integrity of materials subjected to thermal and mechanical stresses, especially in high-temperature applications such as turbines, pressure vessels, and other critical infrastructure. Prevention and mitigation based on API 571. The first is minimize localized temperature excursions. The second is fired heaters require proper burner management and fouling/deposit control to minimize hot spots and localized overheating. The third is utilize burners which produce a more diffuse flame pattern. The fourth is in hydroprocessing equipment, install and maintain bed thermocouples in reactors and minimize the likelihood of hot spots through proper design and operation. The fifth is maintain refractory in serviceable condition in refractory-lined equipment. Short-term overheating and subsequent stress rupture damage in materials, particularly in high-temperature applications, can lead to significant failures in engineering components. To prevent or mitigate these issues, several strategies can be employed. Number 1 is material selection. The first of material selection to be considered is use of high-temperature materials. Select materials that have high-temperature resistance and good creep properties for applications that operate in elevated temperatures. The first of material selection to be considered is alloying. Consider using alloys that are designed to withstand higher temperatures and resist oxidation and corrosion, specifically designed for high-temperature environments, such as nickel-based superalloys, can be more resilient. Number 2 is design considerations. The first of design considerations to be considered is design for thermal loads. Ensure that the design can accommodate thermal expansion and contraction. This includes proper supports and clearances. The second of design considerations to be considered is stress distribution. Design components to minimize stress concentrations which can exacerbate damage from overheating. Number 3 is thermal management. The first of thermal management to be considered is control operating temperatures through active cooling systems, heat sinks, or insulation to prevent overheating. Insulation. Use proper thermal insulation to prevent heat loss and ensure that components do not inadvertently overheat due to external heat sources. Heat sinks or shields. Incorporate heat sinks or shields to protect sensitive components from excessive heat. The second of thermal management to be considered is regularly monitor operating temperatures and system variables that could lead to overheating. Number 4 is loading conditions. Avoid sudden changes in loading conditions that can lead to spikes in stress. This could include implementing gradual load applications or using dampeners to absorb shocks. Number 5 is inspection and maintenance. The first is to perform regular inspections to identify early signs of damage or wear. Employ non-destructive testing methods to monitor the integrity of materials. The second is to establish a maintenance schedule for components exposed to high temperatures to replace them before failure occurs. Number 6 is operational procedures. The first is to develop and enforce operational limits to ensure equipment doesn't exceed specified temperatures and pressures. The second is to train operators to recognize conditions that lead to overheating and how to respond effectively. Number 7 is protective coatings. Use thermal barrier coatings or oxidation-resistant coatings that can help protect the underlying material from high temperatures. Number 8 is stress relief techniques. Utilize stress relief heat treatments, if applicable, to reduce residual stresses in components before they are placed in service. The following stress relief treatments are commonly implemented. The first is post-weld heat treatment. If welding is involved, apply post-weld heat treatment that can relieve stress and reduce the risk of rupture. The second is annealing. For materials that may have been subjected to high-stress conditions, an annealing process may help to relieve internal stresses. Number 9 is redundancy. Design systems with redundancy, so if one part fails, the remaining components can maintain functionality, reducing the risk of catastrophic failure. Implementing these strategies can help in reducing the risks associated with short-term overheating and stress rupture damage, thereby enhancing the durability and reliability of components in high-temperature applications. Inspection and monitoring based on API 571. In fired heaters, visual observation, infrared, or IR, monitoring of tubes and tube skin thermocouples are used to monitor temperatures. The second is refractory-lined equipment can be monitored with heat-indicating paint and periodic infrared, IR, scans. Inspect for refractory damage during shutdowns. The third is maintain and monitor reactor bed thermocouples as well as reactor skin thermocouples. Short-term overheating and stress rupture damage in materials, especially in high-temperature applications, like gas turbines or power plants, can lead to significant failures. Inspecting and monitoring for these types of damage is essential for maintaining structural integrity and operational safety. Here are some common inspection and monitoring methods used to detect these conditions. Number 1 is visual inspection. The first is visual inspection is surface examination. Regular visual inspection can identify obvious signs such as discoloration, oxidation, or surface cracking. The second is visual inspection is infrared thermography. This non-destructive technique uses thermal imaging cameras to detect temperature anomalies indicative of overheating. Number 2 is non-destructive testing, NDT, techniques. They are: the first is ultrasonic testing, or UT. Utilizes high-frequency sound waves to detect internal flaws, such as cracks or voids that may have developed due to overheating. The second is eddy current testing, or ECT. Useful for detecting surface and near-surface defects, it evaluates material conductivity and magnetic permeability changes caused by damage. The third is magnetic particle testing, or MPT, effective for identifying surface and near-surface discontinuities in ferromagnetic materials. The fourth is dye penetrant testing, or PT. Reveals surface cracks by applying a penetrant dye and detecting where it seeps out from defects. Number 3 is metallurgical analysis. The first is microstructural examination. Sampling and microscopy can reveal changes in microstructural features, such as grain growth or phase changes due to overheating. The second is fractography. Analyzing fracture surfaces can help determine the failure mode and the presence of stress rupture damage. Number 4 is mechanical property testing. The first is tensile testing. Evaluating material properties can identify reductions in strength or ductility indicative of damage due to overheating. The second is hardness testing. Changes in hardness can reflect material degradation and the presence of stress rupture. Number 5 is monitoring systems. High-temperature strain gauges. Monitoring strain in real time can detect abnormal deformation patterns that may indicate temperature-induced stress. The second is temperature sensors. Regularly monitoring operating temperatures can help identify operating outside of normal limits, signaling potential overheating. Number 6 is predictive maintenance techniques. The first is finite element analysis, or FEA. Simulating conditions to predict when and how overheating might occur can prevent future damage. The second is condition-based monitoring, or CBM. Using a combination of methods for ongoing assessment of material health, allowing for timely interventions. Number 7 is field measurements and data acquisition. The first is multispectral and hyperspectral imaging. Identifying material anomalies by observing spectral signatures can provide insights into overheating and degradation conditions. The second is acoustic emission monitoring, detecting high-frequency sound waves emitted by the growth of cracks or degradation processes. In conclusion, the selection of inspection and monitoring methods will depend on the specific material, operating conditions, and criticality of the component in question. Regular monitoring and a combination of these techniques can provide a comprehensive approach to detecting short-term overheating and its related stress rupture damage. Thank you.